A sequence is an ordered list of numbers. We call those numbers terms in the sequence. Sequences can be finite or infinite. Can anybody remind us what's the difference between a finite and an infinite sequence? Like, what does it look like? How does it look different? The dot, 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 right? So how can you tell if we're talking about a finite sequence or an infinite sequence? If it's infinite, we'll put a dot, dot, dot at the end of it, meaning just keep going, right? If we don't put the dot, 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 then we mean that's the last term that we're talking about. Okay, now you're going to fill in some information. We're going to consider a sequence to be a function whose domain is the set of positive integers. And instead of a regular function notation, we're going to use something called subscript notation, which fortunately you've seen before in Algebra 2. So I'm just going to clarify a couple of things here. When I say a function whose domain, I'm talking about inputs, is positive integers. What's the first positive integer? 0 is not positive or negative. 1. 1, 2, 3, 4, 5. And those positive integers represent the numbered term that we're talking about. So we're talking about the first term, second term, third term, fourth term. Okay? Instead of function notation, so remember function notation is your f of x or what we might call y. We're going to use something called subscript notation. Do you remember these guys? A sub n. A sub n is just like f of x. Okay? It just is like a signal. Think about it like in terms of a sequence. And so where f of x is your output and x is your input, over here n is our input, a sub n is our output. And so a sub n is our f of x, n is our x. So when I talk about these inputs for domain, these are your n's. So n's are going to be 1, 2, 3, 4, 5 for all sequences. The a sub n's will change depending on what the rule for the sequence is. And if you were to graph a sequence, your horizontal axis would be your n's, because those are your inputs, those are your x's. Your vertical axis would be your a sub n's, or your outputs. And one thing special about graphs for sequences is in mathematics we call them discrete graphs, meaning you would just plot the points for each term, but you would not connect the dots, because there is no 1.5 term. There's only a first term and a second term. There's nothing in between. All right. This graph that I've drawn looks kind of linear, right? I tried to make it linear. That's the type of sequence you guys are going to talk about tomorrow in the video. It's called arithmetic. And it's just like when you add or subtract the same number every time, so that same number acts like a slope. So just kind of as like a heads up about tomorrow. You'll feel better tomorrow when everything's the same. All right, at the end of that slide in your notes, it says, just really quickly, the function values a sub 1, a sub 2, a sub 3, those are called your terms. So remember, n is what number of term you're talking about. A sub n is the actual term. So if you see a sub 5, that's the 5th term. And then I put a note here. I don't want you to worry too much about this. Sometimes things start at 0. When we're doing it together and you're working on assignments and you're writing out your own rules, we'll always start at 1. But don't be alarmed if somewhere on your homework the book starts something at 0. Okay? Then start at 0 and move on. Okay? But for most of us, we'll consider those positive integers starting at 1. Okay, so the next example, super easy. I give you, we call this a rule. The equation is a rule for the sequence. It's how you get the terms of the rule. And we would actually call this an explicit rule. Explicit just means I could ask Peyton, what is the 100th term? And just using that rule, Peyton could easily give me the 100th term. And then I could say, Turner, what's the 50th term? And Turner can give me the 50th term. Any idea how they'd go about doing that? Plug that number in for n, right? So if Turner wants the 50th term, plug n equals 50. If Peyton wants the 100th term, plug in n equals 100. So if we want the first 5 terms of the sequence, we're going to start by plugging in 1. Okay? So a sub 1 equals 2 times 1 plus 1, which is 3. A sub 2 is 2 times 2 plus 1, which is 5. A sub 3 is 2 times 3 plus 1. Oh, that's 7. I'm starting to see a pattern here. So what's a sub 4? And a sub 5? 11. Again, that's arithmetic. We're going to talk more about those tomorrow. They're linear, right? It has a slope of 2, so they're each going up by 2. Now, the last thing I would do is always, like, if I'm asked to list off the first 5 terms of a sequence, I would write them in the list. So I would say the first 5 terms of the sequence are 3, 5, 7, 9, 11. So that it looks like a sequence you would be given. Okay, now 2 and 3, if you'll just glance at them real quick, they look very similar, right? To each other. Small difference. Kind of look at it. I'm going to do the first value with you, and then I'm going to let you and your groups come up with the next values for the sequence. We want to do the same thing, list the first 5 terms. So I'm going to start with number 2. I'm going to do a sub 1. In my numerator, that's 3 times negative 1 raised to the first. And then I'm dividing by 2 times 1 plus 1, but do you recognize that's number 1? That's the same sequence. So what was the first term there? 3. How many times 3? Can you do 2 times 1 plus 1 down there? Yes, if you want to. And you have to do the exponent first. So negative 1 to the first is negative 1 times 3 is negative 3. So you might reduce that as negative 1. Now, I want you and your group members to do a sub 2 to a sub 5. And then when you get those done, I want you to switch gears and look at sequence number 3. And we're going to look at those 2 sequences. Does anything change? If so, what does? I'm going to come peer over your shoulder like the annoying math teacher that I am. Because I love you. You have to do negative 1 times later is negative 1 times negative 1. Careful on that. Oh, okay. What's the difference? And then you actually have to plug 2 in. What is the thing that's going to be the second term of the Remember to move on to sequence number 3 once you get done with sequence number 2. It doesn't matter to me right now.
Miss Crocky.
I feel like I'm in trouble. This is Miss Frankie. Hi. Good, thanks. Yes. Okay, but those yours, just take all your things. They are leaving. You can get the notes on.
Okay. Nobody in for.
Did that take you over 5?
Yeah.
That's what I was already for. I'm sorry.
Okay, so I went ahead, after looking over everyone's shoulders and stealing some answers from you guys, I went ahead and, oops, I got one of those wrong, wrote down the first 5 terms as I saw them around the room. And some of you, like, we simplified the first one to be -1, and you may have simplified 3/9 to be 1/3, totally fine. Let's just talk about patterns. Before you simplify, what do you notice is happening in the numerator of that sequence? The only thing that changes is the sign, right? It's 3 or -3, 3 or -3. It just depends on the power of the value of the exponent. And then in the denominator, remember, that's really the same sequence from number 1, so it's just going 3, 5, 7, 9, 11 when you're doing 2n plus 1. What did I do?
You just copy your answers.
I copied.
So it's alternating signs, so then the 1/3 is 0.
Oh, yeah, okay, thank you. Okay, so this is -3/7 is right. 1/3? -3/11. Yes, thank you. Okay, and then did anybody get to sequence 3? What was different about sequence 3? The signs changed, right? So if you find the first 5 terms for this sequence, you're going to get a +1, a -3/5, +3/7, -1/3, and +3/11. What do you attribute that to? The n plus 1 in the exponent. Okay, so this is a valuable tool we can put in our toolbox, and we can pull out when we want to write a sequence that is alternating signs. Okay. If you want it to start negative, then you would want to start with -1 to the end, because you'll start with the first term. -1 to the first is always going to be -1. So this one's going to be negative, positive, negative, so on. Okay. If you need your first term to start positive, then you're going to use this form, -1 to the n plus 1, because when you plug in 1 for your first term, you'd really be doing -1 squared, which is +1. So this is going to give us positive, negative, positive, so on sequence. Now, on this one, you could really do n plus 1 or n minus 1. They're both going to give you positive for the first term, so either one is acceptable. Okay. But remember, that's a little tool you can pull out if you want terms to change signs. Okay, so on the next slide, you have 2 sequences. And this is where you take a deep breath and you believe that you are very smart, because you are. And you are going to come up with the rules or write the expression for the nth term, a sub n, of the sequence. So you and your table groups are going to try to come up with a sub n equals rules. Now, what I would suggest you do with your group members is look at the sequence, determine the pattern, and decide how you can write that pattern so that I could ask you, what's the 100th term? And you could just plug in 100 and get the 100th term for your sequence. Try something. If it doesn't work, rework it. Okay? I'll give you a few minutes, so go ahead and get started. Look for patterns.
It's a fair rule.
What pattern are you noticing for number 4? Okay, you're adding 4 every time. So what are some people thinking about for their rules instantly? Okay, instantly I would think people would think about something plus 4, right? The problem with that, you're going to do n plus 4, is how many times are you adding 4? 1 time. But if I were to go all the way to the 10th term, think about like from the first term, wouldn't I have to add 4 a lot of times? Okay, so rethink about this. What is repeated addition in math? Multiplication. So if you want to add 4 lots of times, aren't you multiplying by 4? You add 4 twice, you're really adding 8. You add 4 3 times, you're really adding 12. You add 4 5 times, you're really adding 20. So go with this idea of repeated multiplication is, repeated addition is multiplication. Build off of that. 4 times. Then let's work patterns in number 5 and hint hints. You might look at your warm-up sheet. For number 5. When you get there. Oh, I see.
Minus 1 to the negative 1 times n plus 1 to the n plus 1. We just did that. Looks like.
So how do you get there? How do you decide what that Okay, I am going to interrupt, and I know some groups may not be totally finished, but that's okay. After we had our talk about repeated addition, it's really multiplication. So if we were repeatedly adding 4, we're really multiplying by 4. A lot of groups instantly, okay, 4n minus 3. Okay? Because when you start writing that rule for your first term, a sub 1, if you just do 4 times 1, you'd only get, or you'd get 4, but the first term over here is really 1, so we have to subtract 3 from it. Okay. Now you could test your rule to make sure that it works for some other terms. So I'm going to do a sub 4. 4 times 4 minus 3, that's 16 minus 3, and that matches my fourth term over here, which is 13. Okay, so I'm convinced I wrote the correct rule. Remember, that's linear, right? It's like a slope of 4, so you just do 4 times n. All right, what are some patterns that you're noticing in number 5? What's that? Okay, it's changing. Positive, negative, positive, negative. We just talked about that. That's a little tool we can pull out of our belt. We're going to write that as negative 1 raised to the n plus 1. Could be n plus 1, could be n minus 1. All we need is for when we put in n equals 1, we need to have an even exponent so it turns out positive. Okay, so that takes care of my alternating signs issue. And now I just am focused on the numbers 2, 9, 28, 65, 126. Was anybody able to find a pattern for those numbers? It's n cubed plus 1. What n cubed is your perfect cubes, right? I said, look at your warm-up. You wrote down a list of perfect cubes in the warm-up. 1, 8, 27, 64, 125. Now you're looking at 2, 9, 28, 65, 126. You're just adding 1 to those perfect cubes. So you want to multiply this change of signs by n cubed plus 1. Ta-da, you wrote the rule. So you might, when you're looking at your homework tonight, you might want to think about, simplifying the sequence in your mind, like, I see the changing signs. Let me write that down. Then let me focus on the numbers. Okay, and remember, perfect squares, perfect cubes. You also have powers, 2 to the n, that you might think about. There's different ways to write those. Okay. All right. Let's move on to a recursive sequence. So I think there's some things for you to fill in maybe for recursive sequences. In a recursive sequence, you're going to define the first term, meaning you're going to give what the first term is. Sometimes you might get more than the first term. You might get the first and the second term. It all depends on the sequence. The second part of a recursive sequence is you have to describe how subsequent terms are related. So what's really important about the recursive sequence is you need the term before to find the term that you want. So you're just like building off of the term before it. I've got an example, number 6 right there. Notice my first line of number 6 is giving me my first term. So a sub 1 is equal to 6. If I want to find the first 5 terms of this sequence, I already know the first 6. Now I want to find, this is a sub 1, I want to find a sub 2. So a sub 2 is equal to, notice in this notation you've got this a sub n minus 1. So my n here is 2, 2 minus 1 would be 1. So I want the first term plus 1. And then what is the first term? Plus 1, so 7. If I want the third term, then I'm going to take the second term plus 1, and the second term is 7 plus 1, so I'll get 8. So this recursive formula is more like what we instantly said when we thought we were adding 4 every time. We wanted to write n plus 4. That would be okay if you wrote it as a recursive formula, but the trouble with the recursive formula is if I ask for the 100th term, what do you need? The 99th term. Okay. So this notation right here, this a sub n minus 1, this is the term before, I always say. So in order to get any term in the sequence, you need the term before it, and if you only need to list the first 5, that's not a terrible idea, but if we're going for a term later on, we probably want an explicit rule. So my other terms would be 9 and 10, right? Just add 1 to the previous term. Okay, so let's look at another example. A sub 1 equals 3, a sub n equals negative a sub n minus 1 plus 5. We're going to write the first 5 terms in a sequence. Well, the first term is 3. Now I want to get a sub 2, so I'm going to do negative the term before, which would be a sub 1 plus 5. N is 2. 2 minus 1 is 1, the term before. And then what is the first term? 3. So it's negative 3 plus 5, which gives me 2. To get the third term, a sub 3, I'm going to do negative the term before, which would be the second term. Add 5, and that's going to be negative 2 plus 5, which is 3. I can go off of this third term right here, a sub 3. To get a sub 4, I'm going to take negative 3 plus 5 and get 2. You catching on to a pattern there? Next term is going to be 3. So that recursive rule tells me to do 2 things to the previous term. Make the previous term negative and then add 5. So if I start with my first term of 3, I'm going to make it negative and add 5. Negative 3 plus 5 is 2. Then to get the next term, I'm going to make this term negative and add 5. Negative 2 plus 5 is 3. And then I'm going to do it again. Negative 3 plus 5 is 2. Negative 2 plus 5 is 3. And it'll go on. Don't be scared by recursive formulas. If they have more than one first term, you're going to get some more subscript notations. But just think about what those n minus 1 and n minus 2's mean. Just means the term before or 2 terms before. So here I know a sub 1 is 4 and a sub 2 is negative 2. So if I'm making a list, I already have my first 2 terms, right? To get my third term, a sub 3, I'm going to do a sub 3 minus 1, which is a sub 2, times a sub 3 minus 1, which is a sub 1. 3 minus 1 is, or sorry, 3 minus 2 is 1. So this is just saying the term before and 2 terms before. What the minus 1 and the minus 2 means. A sub 2 is negative 2 times 4, so my third term is negative 8. To do the fourth term, what 2 terms am I going to multiply together? Fourth term. The term before and the term 2 terms before. A sub 3 and a sub 2. I already know what those are on my list, so that's going to be negative 8 times negative 2, which is 16. And then to get the next term, I'm going to take a sub 3 times a sub 4. I've got my list going right here. Negative 8 times 16 is negative 128. That gives me a sub 5. For some reason, people make recursive formulas really, really hard, and that should be really, really easy. You have to use the terms before. And then you just do whatever the second line tells you to do. Okay? Does anybody have any questions or clarifications I can make about a recursive sequence or rule? Okay. Does anybody know the name of this sequence? 1, 1, 2, 3, 5, 8? Oh, not Pascal. Ooh, I love Pascal. We'll get there. We'll get there soon, Gracie. It is this semester. Oh, it's sad. Nobody knows this.
I know what the thing would be, the rule would be.
Oh, what's the rule?
And then, or A of
A sub n.
A sub n minus 1 plus A sub n.
What's Bailey trying to tell you to do? Add the two previous terms, right? Add the term right before and add the term 2 terms before. So A sub n is equal to A sub n minus 1 plus A sub n minus 2. And we would, if we were doing the recursive rule, say that A sub 1 is 1 and A sub 2 is also 1. So if we wanted to get A sub 3, we would add these two terms together. 1 plus 1 is 2. Then 1 plus 2 is 3. 2 plus 3 is 3 plus 5 is 10. Now, Fibonacci is super cool. Take my word for it. For right now, hopefully we'll have a little bit of time this semester where we could watch a quick video about Fibonacci because it's awesome. If you didn't know. Okay? You don't need to know a whole lot about Fibonacci. I just think that Fibonacci is so cool I wanted to put it in my notes. Okay, last thing we want to talk about. Summation notation. Oh, yeah! Woo-woo! Summation notation. I heard those cheers. Is there anyone that does like summation notation? Yeah, Miss Cronky. You guys are scaring other people into agreeing with me. Okay, summation notation. Do you remember this Greek letter sigma? Okay. Sigma, when you see that, and if you do any work in Excel, you see sigmas too in Excel in some of the calls to do things in Excel. The thing that I always remember about sigma, and no matter where I see it, it oftentimes calls for me to take things and add them all up. So you know how mathematicians can sometimes be lazy, or maybe we all just want to get a standard language that we all speak. Anytime we write with that sigma, we're saying add all these things together. That's what sigma means. So that's what's on the other side of the equal sign. A sub 1 plus A sub 2 plus A sub 3. Add all the terms. Now, on this other side, back with sigma, you've got some numbers on the top and the bottom of sigma. These are called your lower bound and your upper bound. And they just tell you when to start and stop. Right? So if I equals 1, that's my lower bound, then the first term I start with is A sub 1. And if n is my upper bound, then I have to add all the way to A sub n. So if it's from 1 to 5, I have to add the first, second, third, fourth, fifth terms. And so it's just telling you how many terms to add. And then this piece right here, this A sub I, this is just the rule for the sequence. So just like those things you were writing for me, like the 4n minus 3, I could pop that in right after the sigma, and because my i's have I there, I'd write 4i minus 3. And then if my lower bound was 1 and my upper bound was 5, I would just calculate those first 5 terms and add them together. Okay, so that's all that sigma notation is doing. It's telling you what to do without giving you words to do it. Let's look at some examples so we know what to do when we see those on our homework. Number 9. The sum of the second to fifth terms for the sequence 3i plus 2. It's telling me where to start, so the first term I need is the second term. And to find the second term, I use the rule 3i plus 2. 3 times 2 plus 2 is 8. And then I need the third, fourth, and fifth terms to my upper bound. So I would do 3 times 3 plus 2, that's 11. 3 times 4 plus 2, that's 14. Oh, I'm noticing a pattern. What's happening? Adding 3, so my fifth term is going to be 17. And remember, this is just a call to take those terms, instead of just listing them out as a sequence, this is saying add them all up. So 8 plus 11 plus 14 plus 17. That's 50. When you see sigma or summation notation, you should get like one final number and that's the sum. I am not going to take time to do this second example, but it does have the factorial in it. So does anybody remember how factorial works? If I give you 5 factorial. Okay, we said 5 times 4 times 3 times 2 times 1. If I gave you 4 factorial, 4 times 3 times 2 times 1, right? Okay. All right. One thing to note, and maybe write this down in case you see any factorials in the homework assignment, 0 factorial is equal to 1. 1 factorial is also equal to 1. And then you do your 2 times 1, 3 times 2 times 1. 0 factorial is equal to 1 because the factorial represents the number of ways you can arrange a certain number of items. And if you have 0 items, there is one way to arrange them. You don't. It's a story. So 0 factorial is not 0. That's the important piece of that. We're going to move on and talk really quickly about series. The nice thing about series is series are the sums. Okay? So series and sum, I use those two words interchangeably. Find the series, find the sum. A series has addition signs in between the terms instead of the commas. Okay, so you're adding things up. It can be finite or infinite. And anytime the book talks about an nth partial sum, that's the sum of a finite series. Okay? So if it gives me the nth partial sum, then n is my upper bound. And that's a partial sum. If I see in my upper bound that I have an infinity sign there, that's an infinite sum or infinite series. And not all series have a sum if you go to infinity, but some do. Okay? So you might see some that are infinity and you should not be alarmed. It just means infinite sum. In your homework, you're going to see something like that last example on the page that gives you 2 directions. First it says, find the third partial sum. So when it says the third partial sum, what's your upper bound? 3. So if I were to do that piece, I would change my notation to be lower bound 1, upper bound 3. I'm finding a partial sum. It's going to stop. And that would be for 4 over 10 to the I. So I want to add 4 over 10 to the first, plus 4 over 10 squared, plus 4 over 10 cubed, plus 4 over 10 to the 4th. Now these work out nicely because they have a denominator of 10 here. That would be 0.4 plus 0.04 plus 0.004 plus 0.0004. Oh, you're right. I do only need 3.
Oh.
I think I got stuck on that 4. Sorry, thank you, Taylor. The 4 in the numerator was tricking me. It should only be 3. And then, could I add those up? 4, 4, 4. So that's the partial sum. Okay, if I want to do the second piece of this, which is the sum, that would be to infinity. So this one would go further. 10 to the first, 10 squared, 10 cubed, and I keep going, right? I'm going to put a plus dot dot dot. What's that going to get close to? Or what's that going to be? Point 4. Repeating. So our infinite sum is 24. Repeating. Thank you. And I'll accept the repeating here in sequence and series. Okay? All right, so you have a homework assignment, and I won't be here tomorrow again, remember? So I'll try to leave the answer key to the homework, so during work time, if you want to check some answers, you can. But know that we'll go over some questions when I return on Friday. You could also come see me Friday morning if you want to, if you have questions. Know that I think sequences and series get better after today, because tomorrow is only the sequences that you add or subtract the same number every time. So that'll make it a little bit easier. Have a great day.